All right, Lenz's law is kind of confusing. If we have a coil, if we change the magnetic field in that coil, that's going to induce a current in the coil. If I had a little light bulb attached to this, the light bulb might flash on. If I had a voltmeter, the voltmeter would twitch one way or the other to indicate the direction. What Lenz came up with is the direction of the electricity induced in the coil. That electricity creates its own magnetic field in the coil, basically turns the coil into an electromagnet. The direction of that magnetic field opposes the change that made it in the first place. So let's say I take the north pole of this bar magnet and I stab it into the coil. There's two ways to kind of get the direction. I'll talk you through both of them, and then whichever way sort of resonates for you, you don't have to know both ways, just be able to explain the direction. So let's say we stab a north pole into that. It's as if the coil doesn't like that. It doesn't want there to be a change. It's going to oppose the change. So if the change was we stabbed a north pole in, the electricity is going to flow in this coil to try and repel that north pole away. If it's trying to repel that north pole away, that means magnetically it's going to make a north pole, kind of an electromagnet north pole here to repel that north pole away. If it's making a magnetic north pole here, that means the field lines are coming up and out of it. In grade 11, in the document we talked about the butterfly pattern. The field lines created by the coil are going to point that way. They go through the coil pointing to the right. For this first question I asked about the negative flow, so that means is use your left hand, point your thumb in the direction of the magnetic field. I'm getting that the opposition is my left thumb has to point to the right because that's going to oppose the stabbing of the north pole. That means my fingers are curling this way. So if I had to draw it, the negative flow is going away or into the page above at the top of the coil, or out of the page or towards me at the bottom of the coil. So if I had to draw it, I would draw the current as away from me at the top, so that's X's in this part of the coil, and dots down here. Or if I just wanted to put an arrow, if I was drawing it on paper, I could draw an arrow. Electrons would be going towards the top of the page when they're close to me. That's the logic of Lenz's law. Another way to think about it, let's get rid of all this. So if that explanation kind of bugged you, here's another way. Let's say we're stabbing a north pole in. Before we stab the north pole, there are no field lines in that coil. It's just an inert, just a coil, just a lump of wire really. When we stab the north pole in, all of a sudden we've added field lines. The field lines we've added in that coil happen to be pointing out of the north pole, so they're pointing to the left. So we've added field lines that are pointed to the left. The coil doesn't like that. It doesn't like you adding field lines, so it tries to cancel those out. If we've added field lines pointing to the left, to cancel that out, the electricity in the coil is going to create field lines that are pointing to the right. To create field lines that are pointing to the right, the question asks for negative flow. Use your left hand, point your left thumb to the left. We get the same basic answer. The electrons are going into the page above the coil, out of the page below the coil, and up when they're closest to us. Those are kind of two explanations for the same effect. Whatever one kind of works for you, use that one.